So we're going to say, in general, that a 1 unit, well, actually I should say it this way. For each 1 unit increase, and I'm having trouble with the video, so this is actually the 3rd time I've done it. For each 1 unit increase in X, and that's our predictor variable, our response variable Y increases, or it can decrease if the slope is negative by B units. And again, this is the units of X, this is the units of Y. In this case, they're the same. So for each 1 point increase on the ALEX test, the first exam score increases by 0.59 points. Okay. So an increase of 10 units would increase it to 5 almost 6 points. Okay, so what about those crazy outliers? So first I want you guys to look at the point 6659. That's 66 on the ALEX test. Oops, it's over a little bit. And 59 on the first exam. That's this point right here. Now you'll notice that this is kind of far away from the rest of the data. The rest of the data is all up here. But this point is down here really low. So what's happening is you can see what this is doing. This is actually pulling the slope on this side down like that. And you can really see it. It's really marked if you look at these 2 data points right here, where it's really a lot lower than in here, but here it's right in the middle of the line. It kind of goes, the line actually goes right through them. So this particular point is actually changing our regression line quite a bit. That's why we call it an influential observation. And you can see how much the line moves. It doesn't look as marked over on this side. It looks almost the same over here. So it looks like it actually increases the slope just a bit. Okay, so having that said, I removed it just to look at it. However, I didn't permanently remove it because I don't want to remove an outlier. I'm still going to keep all my data points. This is still going to be the one that I use, unless I have a good reason to believe it's not right. The fact of the matter is that someone did that score, and that means something. That's part of my data. I can't just throw it out willy-nilly. I could decide, oh, hey, that one's kind of a different score. If I had gobs and gobs of data, maybe it would be okay to take one that did not look right at all, that was completely different than the rest of them. But again, it's part of the data, and it's not something that I really want to take out. And then, so let's talk about predictions on a regression line. So let's say that I had a student that got a 115 on the ALEX test. Could I find their expected score? Well, the answer is right here. And the answer is no, because look what I would have to do. So let's just, this would be about 95, 100, 105, 110. 115 would be pretty much on the edge of my screen here. So I would have to extrapolate outside the data that we have available. I can't do that. Oops. Just went way up on me. I can't go, oh, I want to know what's going on over here, because I don't have any data out there. I don't know what's going on. What happens after this? Does it go down? Does it go up? I don't know. I have no idea what happens after that. I don't think it goes down. But does it level off maybe? I don't know. You know, I imagine at some point it would have to, because the maximum I could do on that test was 105. So it would have to. It'd have to stop at some point. Or that would be 105 this way, but yeah, on the x-axis. So it would have to stop right here anyhow. I don't even know if it would get to it. So it would have to be like this at some point. Okay, but the point is you cannot extrapolate outside the source of the data. And so that means that we're using x values that are much bigger or much lower, because remember I said that in this case our y-intercept doesn't really mean much in this case, because when x is 0, we can't have 40. That doesn't make any sense. When x is 0, it doesn't make sense for someone to get a 0 ALEX test score unless they just didn't take it, and I didn't include people that didn't take it in the study. So I couldn't do that either. So I can't go way below or way above and use x values to predict my y values. I have to use what I have data for, which is right here. Okay. So more no-nos in regression. This is a biggie. Correlation does not imply causation. So one of the big ones that was on the news about this one was the MMR vaccine and autism. This happened for a while. And one of the problems was that children would get diagnosed with autism not very long after their MMR exam, because that is just about the age that usually you start seeing the signs. And what kind of started happening is someone saw a correlation. And they were like, whoa, there's a serious correlation between MMR exam and autism. Correlation does not imply causation. There could have been a number of other reasons. One of them is the proximity of diagnoses that occur within several months of a child getting that MMR exam or that MMR vaccine. But then they did some other bad studies that have been discounted by statisticians in the medical community. But anyway, the point is you want to be really careful to not imply causation just because you have a correlation. One of the most famous examples is if you have the women in the workforce as your X, workforce, and you have as your Y, we're going to have the divorce rate. Well, you definitely have a correlation. Let's say that I took this data from, say, 1950 to 2000. Definitely both of those things raised between 1950 and 2000. Women in the workforce increased, divorce rate increased. But were these things really correlated? Now, a lot of times people go, well, I don't know, when I ask that question. However, what if I changed my X variable? What if I changed my X variable to the price of eggs? Is the price of eggs correlated with the divorce rate? Yeah, from 1950 to 2000, yes. But is the price of eggs causing divorces? As the price of eggs go up, more people get divorced? I don't think so. So this is what I mean by this. You can make absolutely ridiculous correlations. And no, they're not causing each other. That's kind of crazy. So the last thing I want to talk about is this thing called the coefficient of determination. And we denote this by an R squared. That is the proportion or percentage of the variability in Y. So how much Y goes up and down. And that's Y is your response variable. That can be explained by the regression with X. So we know that Y changes, right? Y is this, and then this, and then this, and then this, and then this, right? Depending on what X is. Now, if you have something that kind of looks like that, you kind of have a blob. So really, all you would want to do is just look at maybe X bar and the standard deviation of Y, or Y bar and the standard deviation of Y to analyze this data. However, if I have another variable that may be affecting what the mean Y is, and this time I'm going to do it negative just because I want. So over here with higher values of X, or with lower values of x, I have higher values of y. So this one looks like x is having some effect on what y is. And so we do the regression and we figure out what proportion of this variation, so y changes from this to this to this to this to this to this, right, has to do with x, could be explained by x. And when we do that, that kind of gives us an idea of how important or how useful our regression line is. So we have our r squared. So here, the r squared in our example, so I'll show that to you real quick. So in our example, r squared, and if you go back to linreg t-test, you scroll down to the end, you'll get your r squared, 0.3441. So that's what we have. And that's 34%. So 34% of the variability in y, in test scores, can be explained by the ALEC scores that were taken prior to the course. So 34% of the variability. That's some. That's about a third of it. I'm explaining a third of it. So, of course, there's going to be other things. There's other factors that caused your test 1 score to be different. Being a different person, being sick that day, the amount of work that you did. Who knows? There's so many other variables that go into this. We can explain 34% by the regression, but that's about it. So this is not a very high coefficient of determination. But anything over 50%, we are really happy, especially in the real world. But we can consider the regression useful if we get an r squared over 15%. I know that doesn't sound like a lot, but 15% of our data of our variability getting explained is some of it. We're explaining some of our variability. And in this case, we're explaining a third of it, a little over a third of our variability. So that's something with the regression. So, and that's over just using a y bar and a standard deviation of y. We're explaining some of it. So it is somewhat useful. And there's not any real, like, I can't give you a table saying, well, this is extremely useful and this is sort of useful and this is, it's kind of, it depends on what you're doing. And it depends on some other factors in your analysis, whether you would eventually call the regression useful. Mm-hmm. And then, so next time we're going to talk about the population regression line.